All right, last video of the semester. We're going to do a few friction on a slope examples just to get ourselves going there. So let's get to it. Got four examples to do here. So we've got a ramp 20 degrees above the horizontal. So that's 20 degrees right there. We've got our 15 kilogram block. And what forces do we have? I'm actually going to move this down a little bit so I can draw a little easier. So what I've talked about, we've got FG perpendicular, FG parallel, FN. Okay, and then we have push to start sliding up the ramp. So I got to push up the ramp. Now, which direction is friction going to be? Okay, so if I'm trying to slide it up the ramp, the friction is going to be preventing that from sliding up the ramp. So that means friction's got to be the other way. So we got this other force down here, force of static friction. So to my F net parallel equation, F push minus FG parallel minus FS, right? I can do the perpendicular direction, but it's just going to be tell me that Fn, right, so this is 0 equals Fn minus FG perpendicular, Fn equals FG perpendicular. That's what's going to be most of the time. And we know that FG perpendicular, right, is mg cosine theta. Now, we want to start the block sliding. So that tells us two things. The start the block sliding part tells us that A equals 0 and that Fs is Fs max, which is normal force times coefficient of static friction. And I just found the normal force down there. So now I've got m times 0 F push minus FG parallel is mg sine theta minus mg cosine theta us, and I can start plugging stuff in. Okay, so this is none of these numbers that I've worked out. So 0 equals F push minus 15 9.8 sine of 20 minus 15 9.8 cosine of 20 all times 0.5. Plug all that in, and F push equals 119 newtons. Okay. All right. Example number 2. 5 kilogram block sits at rest on a ramp, elevated at 25 degrees above the horizontal. All right, so we can draw again. 25 degrees. We've got our block. Okay. It sits at rest. All right, so the forces we know are always going to be on there. F are normal force. FG perpendicular. FG parallel. And it sits at rest, so that means there's got to be a static friction force that's opposite, and the only force that's trying to make it slide is FG parallel. So we get force of static friction. Yeah, we could just copy this thing right here, right? This whole bit. So, and in parallel direction we have F net parallel equals static friction minus FG parallel. Now, it's at rest, sits at rest, so this is going to be 0. Fs minus FG parallel. So, we can just plug in for this, right? So we have Fs equals FG parallel, which is mg sine theta. This is going to be, it's either going to be 20.7 or 20.2. I can't really read whether it's 20.7 or 20.2. Let's say 7 newtons. Now notice, this is not the same as Fs max, right? Fs max for this is going to be some larger number. Okay. But the whole point is that, like, right, this is not starting to slide. So if it's not starting to slide, we can't use Fs does not equal Fs max in this problem, right? It's somewhere left in that. Fs is less than. Okay, we can't make that assumption because it's not starting to slide. It's not that point at which it's starting to slide. It's just sitting there at rest. So we cannot make that assumption. Okay. So again, we got a ramp. Block. FG perpendicular. Fn. FG parallel, and it's sliding down the ramp. So kinetic friction is that way. Again, I can copy that same little bit there. This is still true. Right. And because it's kinetic friction, FG parallel, or F net parallel is equal to, I'm going to make down positive this time. Like that's the way it's going, so I'm making that positive. MA equals mg sine theta minus mg cosine theta. Okay. We notice the m's cancel out. So I have acceleration g sine theta minus g cosine theta. Okay. And if I actually plug everything in there, I get an acceleration that is 1.78. I don't get that because I've done this all wrong. I've done this a little bit. No, it's not all wrong. So this is like the thing right here. I can't plug it in because I know if I actually wasn't looking at my notes properly, I would know, right, or thinking about this problem, A is equal to 9.8 sine of 20 minus 9.8 cosine of 20, and I don't know what UK is. That's what I'm trying to solve for. That's okay. I'm going to come back to this equation. I need to get acceleration a different way, and I can get it through kinematics. All right, change in x equals 2, v initial equals 0. Right, it's placed there. It's not like push or anything. It's just placed there. So v initial is going to be 0, and time equals 1.5. With this information, I can figure out what acceleration is using change in x, v initial times time plus 1/2 at squared. If I solve this, I get acceleration is 1.78. And now I can go put this into this equation. So now I've got this is equal to 9.8 sine of 20 minus 9.8 cosine of 20. Okay? All right? And now I can plug everything in. And I get the coefficient of kinetic friction is 0.17. Okay? Look, this happens sometimes. I mean, I shouldn't have in this problem. I got it on my notebook right there in front of me. But it happens, right? You start doing the force stuff, then realize you get stuck. Then you gotta go to the kinematics. That'll happen. It's totally fine. You're almost never gonna waste work by doing one and set it before the other. You just have to pause and come back to it. Okay. Finally, we got this one. 20-degree, 20-meter long hill, fence at the bottom. We're gonna sled. I'm gonna totally switch it up on you guys. We're gonna sled this way. The ramp's gonna be the other direction this time. I know, right? Okay. This time we got a little information. This is 20 meters. This is 20 degrees. And here's our object. We've got FG perpendicular, FN, FG parallel, FK, and it's kinetic friction because it's sliding and we're sliding down, so the force of kinetic friction is back up. Alright, but here's the thing here. You've got two coefficients of kinetic friction. We got two parts. This is a two-part problem. One is the sledding part. Okay. F net parallel is equal to FG parallel minus FK. Yes, I am making down positive. that way positive. This is MA equals mg sine theta minus mg cosine theta UK. I didn't solve for normal force here, but again, it's going to be that same thing. Masses cancel out, and we get an acceleration of 2.43. We also have a displacement of 15. You bail out after 15. The whole thing is 20 meters long, but you bail out after 15, and your initial velocity is 0. Again, we can find final velocity using v final squared equals v initial squared plus 2a change in x. V final is going to be 8.54 meters per second. Now for the second part, this v final, that's v initial. Okay. Right? And I know that one way to do this, so this is probably, there's a couple ways to do this one, but probably the best way is find out where you stop. V final is 0, and I want to find what change in x is. But I'm actually going to do that by finding the acceleration using force. So I have F net parallel is equal to FG parallel minus FK. This is still MA is equal to mg sine theta minus mg cosine theta. Okay. All right. And actually, I'm gonna have to do a little quick math here because I did it a different way, the other way on my in my notes, and so I'll do some very quick math. Sorry for the pause here. And my acceleration is going to be negative 3.09. So again, I can do v final squared plus, or equals v initial squared plus 2a change in x. And again, like a bad teacher, I decided to freelance here. Divided by 6.18. And yeah, this is not good. Not even close. Your change in x is 11.09. Or 11 point, that's not right, 11.8 meters. So, did you stop in time? No, you did not. Alright, just an FYI, this is basically exactly what happened to me when I was sledding when I was about 14. Went right into a fence. Did not go great. Had a bruise on my arm that lasted, that was really, fortunately, that was the only part that got hurt. Had a bruise that lasted for a month or so. There you go. 4 examples of friction. Yeah, hopefully that'll help you. All right.